All right, our next speaker will be Antranik Sefilian. We'll be talking about beyond massless models, interactions between planet-disk interaction in debris disks. Take it away.
Hi, everyone. Thanks for being here. Yeah, I'm Antranik Sefilian. I'm a 51 PECB fellow here actually at the Stewart Observatory. And today I wanted to talk about the recent work of mine regarding vertical structures in debris disks and the important role of disk gravity. Given the talks we had earlier today in the morning, I don't think I have to introduce what debris disks are, but just want to say that, we know that they are common. We also know that they are actually structured, as you can see here in this ALMA gallery from ARCs that Sorka presented. And what you can see if you have a quick look is that some of them, are eccentric, some of them are narrow, some of them are very broad radially and have some substructures within them as well. And I guess what drives theorists or dynamicists working in this field is that motivated by the solar system, where much of our understanding of the giant planet's evolution comes from diagnosing the structures in the asteroid and the Kuiper belt, is that if we understand how planets impose structures on debris disks, then we can invert the problem. And by looking at substructures that we see, we can infer the potential presence of planets in such planetary systems. And we've been doing that for some time, maybe a decade or even longer than that. And what this plot here summarizes is the planet's mass as a function of same major axis. All the black dots are actually planets that we have discovered via traditional methods. And all the color points that you see are some of the inferences of planets that we have based on debris disks that we've observed so far. They are pretty cool in the sense that, they seem to populate an area in this planetary album where we don't know much of planets to date, right? So they exist at, I don't know, tens to hundreds of AUs in same major axis and masses anywhere from few Earth masses to few Jupiter masses. And the hope is that, with JWST in the sky, is that we start detecting at least some of these planets that we've predicted based on studying the structures we've observed in debris disks. But I also have to add, kind of to Katie's point earlier today, is that I guess it's safe to say that the only successful exercise of scribing the debris disk structure to a planet has been the story of Beta Peak. So historically, what happened with Beta Peak is that we first observed the disk in the 80s. We saw the warp in its debris disk, and theorists jumped in, said this should be sculpted by a planet nearby the star interior to the debris disk. And such a planet was actually discovered, decades later from the prediction in 2010. And that is what this animation here on the right is showing. But of course, as a dynamicist, and generally, I guess, as a scientist, our predictions are, as good as our models are. And that brings me to the next point and kind of the point of this talk, which is that I think there's a important theoretical gap in our modeling efforts of planet debris disk interactions, and that has to do with the assumption of massless disks. So what do I mean by that is, surely when we invoke a planet in a system by hand, we do account for the effects of the planet on the planetesimals in the debris disk, but we assume that the planetesimals are massless generally, and so the planetesimals don't back react on the planet, and they also don't perturb each other, okay? And so we assume that debris disks are massless, but at the same time, observationally, we know that they should have some mass. And the mass ranges from anywhere, perhaps few Earth masses to tens or even hundreds of Earth masses, depending on who you talk to. So in the remainder of this talk, I will focus on this particular setup. So just so we are on the same page, I have a star. I have a hypothetical planet, which is on an initially misaligned inclined orbit. And there's a debris disk exterior to the planet. The debris disk initially is just razor thin. It has no structure within it. And we will study what happens once we account for the collective gravity of the planetesimals. I do like my paper and pen, which is why I'm treating this problem slightly simplistically. So what I'm doing is I'm accounting for the effect of the planet on the planetesimals and vice versa. So the planet perturbs the planetesimals perturb the planet, but they don't perturb each other, right? And this keeps everything neat and analytical, and one can actually study the dynamics purely analytically, which is what I've done in this specific paper. I'm not going to discuss the details and jump straight to the results. What I'm showing here is the edge-on view of the disk. This is the surface density, okay? This is early times, and this is late times. And what you see here are the results for a massless disk, what we already know since 3 or 4 decades now. So initially what happens is that the planet launches a warp within the debris disk, but the warp is a transient phenomenon, right? Ultimately, over time, once the warp propagates outward within the disk, it goes away and the disk settles into this kind of quasi-equilibrium state where you get this disk to be fully aligned with the planetary orbit shown with this white solid line here. And it also is characterized with this X pattern that you can see. Now we can ask what happens if the disk has some mass, but it is way less massive than the planet is, okay? That's the second scenario. Initially, again, we see some warped structure being launched within the disk, but ultimately you can see that the disk settles into a different state, right? The warp is launched at the inner edge of the disk, it propagates out, and then once it reaches a certain wall within the disk, that's the place where a secular resonance established within the disk, the warp kind of stalls there, and if you wait forever within the limitations of the model, the warp will just stay there and not propagate outward, okay? So you end up with this situation, and you can also see some other differences, like, there's no longer an X shape, but, one of the arms is curly, and so on and so on. But the warp stops at a certain location. And then if we now increase the disk mass even further and say that the disk is actually more massive than the planet is, then we get a completely different scenario here. Initially, again, something happens, right? Some perturbations, warp-like, but ultimately what you can see is that the disk remains rigid, and oh wow, the disk remains rigid, okay, and it doesn't develop any obvious, warps. I have 3 minutes, which is worrisome. There are many applications of this, but one quick application I wanted to discuss is how we infer planets based on observed warps, okay? This is some debris disk, there's a warp in it, it's observed, measured, and so on. And what I'm showing here is the planet mass as a function of the major axis. And the blue line here is the prediction that you get if you follow the massless disk models, okay? The planet has to lie along this line exactly, otherwise it doesn't work. Now let's repeat the calculation with massive disks. It's more complicated. I cannot discuss it, obviously. Colored regions mean that they are ruled out based on dynamical considerations. But what you end up with is the white region, which is the allowed region where the planet can be, right? And if you compare that with the blue line, the massless disk solutions, what you can see obviously is that the parameter space is expanded, okay? There's a larger combination of masses and symmetries that can work. And if you're closer to the disk, then the planet can actually be more massive than you think if you assume the massless disk. And also another cool thing, which I hope to get to discuss, is that if you go to smaller separations from the star, you can see that many of the lines, which represent non-blue lines representing massive disk solutions, they actually intersect or asymptote to the massless disk calculation, which means if we actually end up finding a planet which seems to be appropriate or predicted as in line with the massless disk calculations, it doesn't mean that the disk is massless. It just means that we were perhaps slightly lucky. And that's the final slide I wanted to discuss. Coming back to Beta Peak, right? We predicted a planet based on the warp. We found it. It matches. But I want to entertain the question if we were lucky finding such a planet, right? What I'm showing here is the warp production time based on the Beta Peak B parameters that we know of as a function of disk mass. And what you can see is that, if I increase the disk mass up to tens or hundreds of Earth masses, then the warp production time doesn't change much, which means that the solutions for the predictions of Beta Peak B are kind of similar whether I assume a massless disk or a massive disk, just because it lies in that weird parameter space. And also we can take away that, given the age of the system of whatever, 20 million years or so, then a disk up to, 1,000-ish Earth masses is actually compatible with the picture that we have for this. And great. Okay, I'm on the summary page. I hope I convinced you that disk gravity is important in planet debris disk interactions, and that is actually the case even if the disk is less massive than the planet. And depending on the disk to planet mass ratio, there are implications for what type of vertical structures we get. And obviously, all of this has implications for how we explain observed structures and how we infer planets based on what we see. So thanks for your attention.
Thanks. Questions for Antranik? Virginie.
I was waiting a sec to see if anyone, because we see each other. We We work at the same institute. There's something I'm actually wondering, so here I can't remember in the study on inclination if the planet would also create gaps further out or additional structure. Is this does this coincide with the drop as the curly X? Can you please remind me?
Oh, sure. Yeah. I mean, in this study, I assumed that the planet is on a circular orbit.
Mm-hmm.
But if I had accounted for, non-zero eccentricity for the planet, as I
Mm-hmm.
have done in my previous papers, then yes, there should be some gap structures as well. How they, how a non-circular and non-coplanar planet would impose a structure on a massive disk, I haven't looked at that, but that's something interesting to look at, of course.
Thank you.
Okay. Online questions?
Yeah, thank you. We have an online question from Katie Krotz. Could your model possibly help explain the beta pig cat's tail?
Yeah, the direct answer is I don't know. But in the paper, I actually say whatever curly X that you see there is akin to what was observed with JWST for beta peak, but whether they are connected or not, I haven't yet investigated.
Okay, we have time for one more question. Okay, I have a question actually. For the mass estimate, what kind of size distribution do you account for? Would that severely affect the estimate in mass, in the dust mass?
Yeah. So I don't care about, how the estimates are done as far as this study is done, right? Because I'm just putting some mass that I can. But usually, yes, I mean, people observe the dust mass and then you extrapolate that to the, total mass of the solids. And that has some, uncertainties in there. Usually people extrapolate based on some size distribution and you can question things there as well.
Thanks. So you're saying that you smear all the mass into particles?
Yes.
Okay, thanks. Okay. If there's no additional questions, let's thank Antranik again. And that concludes the disc